In this video I will demonstrate how to estimate a VAR model, that is vector autoregressive model, or in other words vector autoregression model. Now here is the data. For simplicity, I will just select 3 variables. You can select as many as you want depending on the econometric model you want to estimate. In VAR, if you are estimating unrestricted VAR, you should have the variables differenced if they are integrated of order 1, or they are first difference, requires first difference in order to be a stationary, your data. Now these are the data, series. I will select out of these 6 variables. We will choose let's say 3 of them randomly. Let's take difference of Ly, LGP, and DLE85P. Now we assume that these are variables, econometric variables, and we will now estimate a VAR model for them. When we estimate it, we need to select lag length for VAR, and then we need to check for residual autocorrelation, normality of the residuals, and heteroscedasticity, and then estimate heteroscedasticity tests as well. Then we can have blue coefficients. These are best linear unbiased estimators, which I've almost forgotten a long time. I haven't recorded a video of this type and haven't looked at econometric books, but I hope I remember them all now, step by step. So we selected these 3 variables, random variables, and we will need to now open them as a group, or we can open them as VAR. So that's vector autoregression specification menu here. Now there are 2 types of VARs, unrestricted VAR and vector error correction, or VECM. You need to choose unrestricted VAR because we assume that these 3 variables are not co-integrated, or they do not have long-run association among themselves. So we assume that they have short-run association only, or they cause each other in the short run only. So usually before estimating any VAR model, it's advised that you have to run a Johansson co-integration test, or any other co-integration test that you know, and then test for existence of co-integration. And then if there is no co-integration, then you have to proceed with VAR. And when you enter variables into VAR, they should be first differenced and should be stationary when they are first differenced. So they shouldn't be I1, they have to be I0, the variables here. Now our sample is from 1998 M1 to 2011 M12, and these are the variables, endogenous variables they call it, and we have the lag intervals for endogenous variables. Now we leave it at 2 at the moment. We haven't yet chosen the length of the lag, and you can, if you want, you can enter here exogenous variables like constant, trend. You can also enter any dummies you wish to be included. Dummies needs to be included when you have structural breaks, or when you see the impact of let's say economic or financial crisis. In our instance, we assume that there is no structural change in our data, and we tested for it, unit roots as well, and I have a video on how to do this on YouTube channel, on my channel, ADF test, augmented decay Fuller test. Now we assume we've done this. Now I'll press OK, and it will show us the menu, estimate output menu here, a VAR output menu here, and in this case, in this first column, dly is an dependent variable, and the rest of the variables, including dly itself with the lags for first and second lags, are the independent variables. And in this column, the results or coefficients of other model, and in this model I have dlgp as my dependent variable on these independent variables, including c. And in this model, as you can see, DLE85P now is a dependent variable, while the rest is an independent variable. Essentially what it is if you look at DLY, if you look at the first model, we are trying to see if there are short-term influence on DLY from its own lags and the lags of the other two independent variables. And in this case, now in the second case, we just replaced this dly with dlgp and then did the same thing here. Its own lags here plus the lags of other remaining two variables. Now here are diagnostics output of this VAR model. At this moment we are not looking at this, although r squared is small, pretty small. We will ignore this for now. Usually higher the better, obviously. We might need more lags here to make it higher, but we'll have a look. We'll need to check first for lag length, and the optimal lag length needs to be found here to get the final model. To do this, we go to view, we go to lag structure, and we go to lag length criteria. And since we have monthly data, by the way, this is a monthly data, we include 12 months maximum lag. Usually it's better to do so. In 1 year you have 12 months, so, and then we can go as long as we want, but economic theory suggests that 12 months lags is actually advised by economic theory. Some people argue that you can use 4 lags as well in monthly data, but in fact, if 6 months, the impact of changes in variables 6 months affects at current status of the variable, then alters the current or determines the current coefficient, or determines the current status or the condition of the variable. In that case, it's better to have as many as possible. Usually 12 is advised, but if you have quarterly data, it's advised that you include 4, because in 1 year you have 4 quarters. You can include obviously 6 quarters or 12 quarters. In annual data, again, I would use 1 or 2 lags, not much than that. Usually annual data, you need a much longer period actually. With the monthly data, shorter periods. With the months becomes longer period actually. The sample becomes longer because this is monthly. 1 year divided into 12, and then you have 12 years. You have times 12 by 12, so the square of 12 period will become your or 144 months basically. So that's a sufficient lag. At least 30 is fine usually, but again, depends on the study. Okay, so this is this is outside the topic of today, so we are just digressing a bit, but include 12 lags and press OK. Alright, what we have here are the criteria and likelihood ratio as well, which shows us 12 lags needs to be included. You have the star here. This one shows us 3 lags. Final prediction error, and IIC shows 3 lags. KIK information criterion, Schwarz criterion shows us 2 lags, and Hanan Queen shows us 2 lags. Okay, usually some researchers say follow LR procedure, follow what LR advises, but I usually follow AIC, although SC and LR, these 3 criteria show pretty much the same results. So let's go with AIC, but you can choose 12 lags and estimate, or sequentially, like delete the lags up to 3 and then see the results. You can do, like, let's say estimate the VAR with 12 lags and estimate is 10, 8, 6, 4, 3, and then look at the results and choose the one which has the best passes the diagnostic tests and has follows, I mean, the data follows economic theory, or the results are meaningful to interpret, basically. But let's, for simplicity and for demonstration, choose 3 lags. We need to now re-estimate the VAR because this is a 2 lag VAR here. So estimate again, go to estimate and then change the lag to up to 3 and press OK. Now you have the results here, and you have 3 equations here. These are the coefficients of the each lagged term. Now what we want is, before we go further to do anything, we want to see if this model is reliable or has blue coefficients, sorry, best linear unbiased estimators, like the coefficients are usually estimators, they call this. So this coefficient is blue, basically. We need to find out whether it's blue or not. So we go to view, we go to residual tests, and the researchers advise that we test for residual autocorrelation using portmanteau autocorrelation test. Click, and lags include 12, and let's have a look. Now you will not see first 3 Q stats because we have 3 lags selected, so it's usually blanked. But then you need to look at these here and see if the null hypothesis of no residual autocorrelation up to lag H is rejected. If it's not rejected, that is good, because in that case we don't have residual autocorrelation. So we don't have a problem of omitted variable. Now there is one here which is significant at adjusted Q stat, significant at 5%, but significant at 10%, but this is one only, so we want most of them to be greater than 0.05. So we can actually say the residual autocorrelation doesn't I mean, there is no residual autocorrelation. Now we go to normality test of the residuals. Actually, you can do autocorrelation LM test as well, Lagrange multiplier test, and see if there is a residual autocorrelation. In fact, this also follows pretty much the same. It shows us the same thing as the other test showed, like, but there's an extra one at lag 9. But what we can do is, since there aren't, I mean, not many, most of them, majority of them still failed to reject, show us that we failed to reject the no residual autocorrelation null hypothesis, then we can go ahead. I mean, we pass this test. Now we go to normality test. Usually this is a minor test in some instances, but some researchers might argue that if you fail to, I mean, if you reject the normality tests, then don't estimate your model because your coefficients are not blue. But look, we actually rejected normality for kurtosis, for skewness, and jointly Jark-Berra test shows that we reject the normality. But 9 times out of 10, whatever model you estimate, you get this sort of rejection because of the data's behavior, and maybe you have short sample. This is not very short sample, but this is not very long as well. 167 what you call this, 167 monthly data, I mean term, not terms, month, 167 periods basically. Now this suggests that maybe there are outliers in our data. Maybe we have structural changes in our data. So if you include proper and identify it correctly the structural changes and included appropriate dummy variables for these structural changes, and I'm sure you will have a better result. So you will probably fail to reject these normality tests if you have the right dummy variables. But in this video I'm not doing this. I mean, I didn't include it because it will take time to test to identify the structural breaks, and to do this if you have one structural break, then you can use Perron's unit root test or Ziot and Andrews unit root test. But if you have more than one structural break, then use by Perron structural change test. So the first two tests are unit root tests. Actually, you should use them if you feel that you have a structural break, but in your data. But if you don't use, then you just simply use ADF or the others that are standardly normally used. Then you might falsely, you might mistakenly reject the null. But they have low power if there is, I mean, they have low power usually if there are structural changes in your data. So it's advised that you do check the check for structural breaks in your data, and then include the right correct dummies, so that your residuals of your model become normally distributed and gives you blue coefficients. Now once we did this, now we have to change. We have to look at your data and then do something with it. But let's go to the next residual test, that is White's heteroscedasticity test. I'll just choose no cross terms. So now if we reject the what you call this, the null hypothesis of homoscedasticity in our residuals. Now we go back to, again, perhaps something needs to be included in our data. It's again this characteristic of the data. There must be fluctuations that needs to be accounted for by the dummy variables. Might be causing this as well, but it's best to look at the data before running the model. Now we assume that we passed this data, this stage of as well, I mean residual test as well, and we just go back to estimation output, and assuming that we passed all the tests, but you can still estimate, I mean you still carry on with this model, but these ones are not right coefficients. In other words, they are not blue. This could be 0.7 rather than 0.63, or this could be 0.85 rather than 0.085. So they are not the blue. Basically, they are not the best ones that you could select. They are from the distribution of this coefficient that attached to this term, but they are not the blue ones. Now, what I wanted is from this model is to test for Granger causality. In other words, Granger causality says if x and y, let's say if y is Granger caused by x, then the past values of x can forecast the future values of y. So given this assumption, we want to test the causality here among our three variables. So we go to view, and we go to lag structure, and I want to go to Granger causality, and this is also called block exogenated test actually. So this is the test result here. Now you have to be interpreting it in a way that is more meaningful. Let's interpret this table first. So this is standard. Now first we look at the first equation. If you remember the first column, in that column we had dly as our dependent variable. Now what it says here is dly is Granger caused by dlgp. This test here, this is a null hypothesis, and this hypothesis states here that the legs of DLGP taken together do not Granger cause DLY. Now that is rejected, as you can see. So it actually does. I mean, two legs. Remember, taken together actually causes DLY. So in fact, they can predict, taken together, they can predict DLY's behavior in the future. So we have causality running from DLGP to DLY here. Now in the second step, we know as the next hypothesis is that taken together all the legs of DLE85P do not cause the DLY in the future. I mean, do not predict the future of DLY, or in other words, the lag terms of DLE85P are equal to 0. So this is a joint hypothesis again of these being 0, and we actually reject them at 10%. So there is a weak evidence, but still a valid one, given that our we passed all the tests, earlier tests. So 0.617. Now, so causality runs from DLE85P to DLY. So there is a unidirectional causality at the moment, so from this to this and from this variable to this variable. Now the next hypothesis test, all means that all independent variables taken together causes DLY or not. In that case, we say all the lagged coefficients of DLGP, DLE85P are equal to 0, but we reject this. So the causality runs from the model to LY, so from all independent. So all the independent variables with their legs can determine DLY or cause DLY. So that's the Granger causality test in the first model. Second, now in this second model equation, DLGP is our dependent variable, and we test that DLY taken together with its legs do not Granger cause DLGP. Now we fail to reject that. In other words, there is no Granger causality to DLGP. There is no Granger causality to DLGP from DLY. However, there is a strong evidence of Granger causality running from DLE85P to DLGP. So there is a unidirectional causality from DLE85P to DLGP. And taken together, these variables do not cause Granger cause DLGP. That's done. Now dependent variable this time is DLE85P, and as you can see, DLEY do not Granger cause DLE85P with its two legs. I think we had the 3 legs, sorry. And however, DLGP, strong evidence here that the DLGP Granger causes DLE85P. Taken together, actually, they do Granger cause DLE85P. Now we need to sum up everything here, what we have just discussed. Now we know that there is a Granger causality from DLGP to DLY, but is there a Granger causality from DLY to DLGP? No. So this is the case here. It's no Granger causality. So there is only unidirectional causality from running from DLGP to DLY. Okay, DLE85P to DLY is a Granger. I mean, there is a Granger causality running from this variable to this variable, but we need to see if there is any. It's the reverse scenario from DLY to where is my DL? Yeah, from DLY to DLE85P. No, so there is only unidirectional causality from DLE85P to DLY here as well. Now, is there a Granger causality from DLE85P to DLGP. Yes, here we go. So there is a there is a unidirectional causality from DLE85P to DLGP. However, is there a reverse causality like DLGP to DLE85P? Yes, here we go. So this is a bidirectional causality here. So there is a feedback effect basically. DLGP Granger causes DLE85P. In return, DLE85P also Granger causes DLGP. So two bidirectional, one bidirectional and two unidirectional causality among our data, and this is short-term causality here we discussed. Now for long-term association, we need to look at vector correction models, which includes the co-integrating equation, long-run equation as well. Now with this I will end the video, and hopefully I will make more videos as I have time in the future. But hopefully this is helpful to you, and if you want to have to leave feedback, you are welcome to do so. And if you have a question, you can also leave them, and I don't promise that I will come back to answer them, although you are correcting me or not. You are welcome to correct me if I've made any mistakes, or if you have questions. Then I don't promise that I will have time to answer each of them, but as I have time, I will come here on YouTube channel and check the status and then situation around the video, whether this is going well or not. So thank you very much, and hopefully see you next time with more videos.